Did you know that within the next decade, quantum computers could break every single encryption code we currently use? Your online banking, emails, even your smart home devices, all potentially vulnerable to the power of quantum computing. This isn't just some distant sci-fi threat. It's a real and pressing issue impacting our digital security right now. Imagine if all your encrypted data suddenly became readable. What would that mean for privacy and cybersecurity? In this video, we'll dive into how quantum computing is revolutionizing cryptography and why you need to care about the next generation of encryption. Get ready to unravel the mysteries behind the technology poised to reshape our digital world. Classical ciphers have been the backbone of secure communications for centuries. These encryption methods rely on mathematical algorithms to scramble messages into unreadable code. One of the most famous classical ciphers is the Caesar cipher, which shifts each letter in a message by a fixed number of positions in the alphabet. For instance, with a shift of 3, A becomes D, and so forth. This simple substitution method was effective during ancient times, but easily cracked today. Another widely used classical cipher is RSA encryption, which relies on the difficulty of factoring large prime numbers. However, as computing power increases, these methods become more vulnerable. According to a study by MIT researchers, quantum computers could potentially break RSA encryption within seconds, rendering it obsolete for secure communications. As we delve deeper into this topic, let's explore how quantum computing is reshaping cryptography and pushing the boundaries of what was once thought unbreakable. Shor's algorithm is a groundbreaking quantum computing method that threatens traditional cryptography. This algorithm can factor large numbers exponentially faster than classical computers. For instance, while it would take billions of years for a classical computer to crack RSA encryption using current technology, Shor's algorithm could do it in mere minutes on a sufficiently powerful quantum machine. Consider how this impacts security. If quantum computers become widely available, they could break the very foundations of internet security as we know it. This is because many cryptographic systems rely on the difficulty of factoring large numbers for their security. With Shor's algorithm, this assumption no longer holds true. As we delve deeper into the world of post-quantum cryptography, understanding these vulnerabilities becomes crucial. Quantum computing is poised to revolutionize cryptography by breaking many classical encryption techniques. Consider RSA, a widely used public key cryptosystem that relies on the difficulty of factoring large prime numbers. Quantum computers, using Shor's algorithm, can factor these primes exponentially faster than any classical computer. This means a quantum computer could potentially break an RSA-2048 encryption in minutes, whereas it would take a classical supercomputer millions of years to do so. Traditional symmetric key algorithms like AES are also at risk, though they offer more resistance due to their design. Quantum computers can use Grover's algorithm to have the effective bit strength of these keys, making them less secure than before. As we delve deeper into this transformative technology, it's clear that quantum computing is not just a theoretical concept, but a looming reality that challenges our current cryptographic foundations. Post-quantum cryptography is emerging as a critical field to safeguard our digital world against quantum threats. Researchers are developing algorithms that can resist attacks from quantum computers, which could potentially break many of today's encryption methods. One promising solution is lattice-based cryptography, where problems like finding the shortest vector in a high-dimensional lattice remain challenging even for quantum computers. Another approach involves code-based cryptography, such as McAleese cryptosystems, which have withstood scrutiny for decades and are now being reconsidered for their robustness against quantum attacks. The National Institute of Standards and Technology, NIST, is currently evaluating multiple post-quantum cryptographic algorithms to establish standards by 2024. These solutions will be crucial as we transition from classical cryptography to a new era where quantum computing poses significant risks. As we delve deeper into the specifics, let's explore how these advanced techniques are being integrated into real-world applications and systems. Hybrid encryption techniques blend classical cryptography's robustness with quantum computing speed. Consider how RSA, a widely used classical algorithm, can be fortified by quantum-resistant algorithms like lattice-based cryptography. This combination ensures that data remains secure against both traditional and quantum attacks. For instance, the National Institute of Standards and Technology, NIST, is currently evaluating several post-quantum cryptographic methods to update its standards. These hybrid approaches not only leverage existing infrastructure, but also prepare for a future where quantum computers might break classical ciphers. By integrating these techniques, we can build a more resilient cybersecurity framework that withstands evolving threats. As we move forward, understanding how these systems interlock will be crucial in safeguarding our digital world. The transition to quantum security isn't without its challenges. One major hurdle is the cost. Upgrading infrastructure to be quantum resistant can be prohibitively expensive for many organizations. According to a report by IBM, 75% of businesses are still in the early stages of planning their quantum-safe strategies. Another issue is interoperability, ensuring that new quantum-resistant systems work seamlessly with existing classical systems is complex and requires significant coordination. Consider the financial sector. Banks need robust security, but also must maintain uninterrupted services during transitions. Look at the healthcare industry too, where sensitive patient data must be protected without disrupting critical care operations. These sectors face unique challenges in implementing quantum-safe solutions. Addressing these obstacles will require not just technological innovation, but also strategic planning and collaboration across industries. As we navigate these challenges, it's clear that a comprehensive approach is necessary to ensure a smooth transition to the next generation of cryptography. Quantum cryptography is already making waves in various industries. Consider China's quantum satellite MISHIS, which has successfully transmitted quantum keys over a distance of 1,200 kilometers, marking a significant leap forward in secure communications. This technology ensures that any attempt to intercept these transmissions would be immediately detected due to the principles of quantum mechanics. Take another example. Financial institutions like J.P. Morgan Chase are exploring quantum cryptography for ultra-secure transactions. They're researching how quantum key distribution can fortify their systems against future threats posed by quantum computers. These applications highlight the transformative potential of quantum cryptography in securing our digital world. As we delve deeper into these technologies, the next frontier is understanding the challenges and limitations that come with scaling up quantum networks. Quantum computing poses a significant threat to our current digital security infrastructure. Traditional encryption methods like RSA rely on the difficulty of factoring large numbers, but quantum computers can perform this task exponentially faster using Shor's algorithm. This means that within the next decade, many of today's cryptographic systems could become vulnerable. Consider how this could impact industries from banking to national defense. Take the financial sector. A 2019 report by McKinsey estimated that cybercrime costs the global economy between $570 billion and $1 trillion annually. The introduction of quantum computing could exacerbate these risks dramatically. As we navigate this shift, it's crucial to understand how our existing security frameworks might need to evolve. Next, let's explore some of the emerging cryptographic techniques designed to withstand quantum attacks. The future of cryptography in a quantum era is both thrilling and daunting. Quantum computers have the potential to break traditional encryption methods that we rely on today. For instance, Shor's algorithm can factor large numbers exponentially faster than classical algorithms, which poses a significant threat to RSA encryption used widely for secure communications. Looking ahead, post-quantum cryptography aims to develop new cryptographic techniques that are resistant to quantum attacks. One striking case is lattice-based cryptography, which shows promise in maintaining security against both classical and quantum computers. As we move forward, the landscape of cybersecurity will be reshaped by these advancements, driving a need for robust, quantum-resistant solutions. The transition from current systems to quantum-safe alternatives will require significant effort and investment across industries. Organizations and governments are taking significant steps to prepare for the quantum threat. The National Institute of Standards and Technology, NIST, is leading the charge by evaluating post-quantum cryptographic algorithms, aiming to standardize them by 2024. This proactive approach ensures that critical systems remain secure in a future where quantum computers could break classical encryption. Consider Google, which has already begun implementing quantum-resistant algorithms in their products. They are testing these new methods to ensure they can protect data effectively against potential quantum attacks. Governments around the world are also investing heavily in quantum-safe solutions. The EU's Quantum Key Distribution project is a notable example, focusing on developing secure communication networks resistant to quantum hacking. As we gear up for this technological shift, it's clear that staying ahead of the curve will be crucial for maintaining cybersecurity. Next, let's dive into how these new cryptographic techniques actually work and why they are so effective against quantum threats. Current research in quantum cryptography is advancing rapidly. IBM has already developed a 53-qubit quantum computer, pushing the boundaries of what's possible. Google claimed quantum supremacy in 2019 when their Sycamore processor performed a calculation in just over 3 minutes that would take the world's most powerful supercomputer thousands of years to complete. These advancements are crucial for developing secure quantum cryptographic protocols like quantum key distribution, QKD. Consider how QKD uses the principles of quantum mechanics to ensure absolute security, making eavesdropping impossible without detection. Research teams worldwide are also exploring post-quantum cryptography methods that can withstand attacks from future quantum computers. This work is essential as we move towards a fully quantum-safe digital world. As these efforts continue, the next frontier will be the practical implementation and integration of these technologies into our everyday systems. The rise of quantum cryptography brings both incredible opportunities and significant ethical challenges. Consider that while quantum computers could break traditional encryption methods, they also offer unprecedented security through quantum key distribution. However, this technology isn't equally accessible or affordable for everyone. In fact, a 2021 report from the National Institute of Standards and Technology highlighted that small businesses might struggle to adapt to these new cryptographic standards, widening the digital divide. Moreover, the ethical implications extend beyond economic disparities. Governments could use quantum cryptography to enhance surveillance capabilities, raising concerns about privacy rights. Picture this. If state actors can decrypt any communication with ease, individual freedoms are at risk. As we navigate this technological shift, it's crucial to establish robust regulatory frameworks and international standards that protect both security and civil liberties. As we delve into the future of quantum cryptography, these ethical considerations will shape how this technology is implemented globally. In today's video, we've explored how quantum computing is poised to revolutionize cryptography. Quantum computers can break classical ciphers in seconds that would take even supercomputers millions of years. For instance, Shor's algorithm could render RSA encryption obsolete. But it's not all doom and gloom. Post-quantum cryptography offers robust solutions. NIST has already shortlisted several quantum-resistant algorithms for standardization, ensuring our digital security remains intact in the quantum age. As we look ahead, the integration of these new cryptographic methods will be crucial to safeguarding information against future threats. The race is on between developing quantum computers and creating unbreakable codes, and it's fascinating to see how technology evolves to meet these challenges head-on. Keep an eye out for more updates as this field continues to develop at breakneck speed.